Welcome. We're starting chapter 7 now, and we're going to talk just about the first part today, which is centripetal acceleration. So we are going to solve problems involving centripetal acceleration today. Today we are going to solve problems involving centripetal force. But what in the world is centripetal acceleration? So to answer that question, we first need to define a few new vocabulary terms and to talk about circular motion first. So here are some words. We have axis, which is a line that divides something evenly, and then to rotate, which means to turn around an axis. So the axis of rotation then is the line around which something rotates. So for example, here we have the Earth, and we all know that the Earth turns. So the Earth has a center axis that runs kind of through where the North and South Pole are, and it turns around that axis. That's the center line that it spins around. So circular motion then is just rotation about a single axis. So the Earth rotating is circular motion. Also, if you took a ball and put it on a string and swung it in a circle, that would also be circular motion. So here are some other, we just mentioned a ball on a string. The Earth rotating through the day is circular motion. The Earth rotating about the sun, going all the way around the sun, that is also circular motion. And wheels on a car spinning around as you drive is also circular motion. So when we talk about circular motion, we can also talk about something called tangential speed. And maybe you remember from math class, but if you have a circle and you have a line that runs along the circle and hits it just at one point, and my drawing skills are not that great. There we go. Right, so this line hits the circle just at one point. That's called a tangent, or a tangent line. So when we talk about tangential speed, it's actually the speed during circular motion if that object was going in a line tangent to the path. So if it went out that way instead of continuing to follow the circle. Okay. So if this tangential speed, if this is constant, we call this uniform circular motion, where uniform means it stays the same. So I want to point something out now about tangential speed, okay? Because we could imagine that these 2 points, A and B here, could rotate about this circle so that they stay on this line as they go about, okay? And so we might wonder which one, A or B, is going faster. Or does the radius, okay, the distance from the center, affect the tangential speed? So I already did some of the work here, and if we assume that this radius 1, is a value of 1, and this total distance is 2, so that B is twice as far out as A, and if it rotates around the whole circle in 1 second, okay, then we can use our equation for speed, right, where speed equals distance divided by time. So speed equals distance divided by time. So I've already calculated the total distance using the radius here. And for radius 1, I get distance 1 here, 2 pi. And sorry I used the wrong color. So then if we use our distance divided by time, our distance 1 is 2 pi meters. And then we have the time of 1 second. So we end up with 2 pi meters per second. Then if we calculate the other one for radius 2, the distance here ends up being 4 pi. So V will equal 4 pi meters divided by 1 second, which gives us 4 pi meters per second. And you can see that a radius twice as far out will have twice the tangential speed. So the further something is from the center of curvature, or where the center of the circle, then the faster its tangential speed can be. So, talking about centripetal acceleration now, okay? So this is acceleration only due to a change in direction, not a change in speed. Okay? So anytime the direction changes and the speed does not, we call this centripetal acceleration. Okay, and we have a unique equation for centripetal acceleration. So centripetal acceleration equals the tangential velocity squared divided by the radius of the curve. So here's an example. If you're riding on a Ferris wheel, right, you just go round and round and round and round. And except for when it stops to let new passengers on, you're always going at a constant velocity. So if we drew the vector of your tangential velocity, it would always be going off like this. Okay, that goes off in straight lines. Okay, so you're rotating around this with a constant tangential velocity. Okay. And we write VT, I don't know if you catch it with a T, because T stands for tangential. And so we have uniform circular motion as you go around this Ferris wheel. Because your direction is the only thing changing because of this constant tangential velocity, that means this is centripetal acceleration. Now when you see the word centripetal, okay, this word here, right, it kind of looks like the word center. And that's because the direction of acceleration for centripetal acceleration is towards the center. So anytime if I drew the acceleration at the same time as the velocity, it would always be going towards the center of the circle, no matter where you are around that circle. So let's look at another example. A ball on a string, okay? A ball on the string is the same thing. We've got a ball on a string, right? And the path that it's going to take is going to be this big circle, okay? At any time, it will have some constant velocity, okay, as long as you keep swinging it at the same speed. And its acceleration will always be towards the center, okay? And you can kind of think about it, if you feel it on a string, right, you have to be pulling on that string. You can feel the tension in it, okay? So you're using a force that causes acceleration towards the center, and so the object follows this curved path. So let's look at a math example now. So if you remember, we had the equation AC equals VT squared divided by R. So as we read this then, it says a dog sits 1.5 meters from the center of a merry-go-round. So R is 1.5 meters. If the dog's tangential speed is 1.5 meters per second, so VT is 1.5 meters per second, what is the dog's centripetal acceleration? All right, so I'm going to put this picture up here in case you didn't know what a merry-go-round is, so you can imagine the dog sitting there. And now we've got our equation already, so we just need to plug things in. So AC equals 1.5 squared divided by 1.5, and that gives us an exciting 1.5 meters per second squared. Okay, notice here the units, we had meters per second, and we squared them, and then divided by meters. Last note for you, okay, we can also have tangential acceleration, which is the acceleration related to tangential velocity. So if you're traveling in a circle, but your velocity is maybe big, and then it's small, and then maybe it gets bigger, and then it's huge, okay? We can also have that tangential acceleration, but we are not going to calculate anything, okay? So we are only going to talk about centripetal acceleration, which is the acceleration that pulls things towards the center of a circle. So we will not be calculating this in our class. So if you have any questions, go ahead and make sure and ask me, and that is our start to Chapter 7.